All right, so now why do we even care about the cross product? Okay, let's talk about this for a second. We learned the definition basically of this cross product thing, right? And we learned that what it was doing is it was taking this vector right here, the u vector, and then multiplying it by the component of v, which is perpendicular to u, right? And that's why when we did this, we said u cross v, or the magnitude or the value of that cross product, is equal to u times v times sine of theta. And remember, it was sine of theta because this was the angle between the two vectors. Sine of theta would give me the opposite over the hypotenuse, so therefore that would give me what I'm looking for, that vertical component of that vector. Okay? Now, if you think about this just for a second, what if I were to extend this? So I'm going to take u and I'm going to draw v over here. And then I'm going to draw u right here. What do I have? I've got a parallelogram, right? And what do I get when I multiply u times the vertical component of v? When I multiply those two values together, I get the area of the parallelogram. Is that snazzy or what? I think that's kind of cool. So what that means is that I can find the area of any parallelogram by knowing the length of one side, the length of the other side, and the angle, because then I can, and not just any parallel, it can be any parallelogram in three-dimensional space, because now I can take these three-dimensional vectors, I can find their magnitudes, I can do the cross product, right? In the previous question, we found a cross product which was this. So if this is equal to v cross w, I can very easily find the magnitude or the absolute value or the modulus of those, right, by doing the v squared plus v1 squared plus v2 squared plus v3 squared, all square root of that, right, to find the modulus or the distance formula for that, okay? And you've done that before. So with that, I can now find the area of any parallelogram in three-dimensional space, which is kind of cool. Now, something that kind of comes from that is not only can I find the area of any parallelogram, I can actually find the volume of any parallelepiped. Now, a parallelepiped is a three-dimensional object that has a parallelogram, two parallelograms for bases, and then basically a prism, a parallelogram prism. So if we kind of do this and that, and then over here it'll go out like this, right? So there you go. That's a parallelepiped. So if these two faces, this one in the front and that one in the back, are parallel to each other, if I can find the area of the parallelogram, I can just take the area of the parallelogram and multiply it by the depth, whatever this vector is. So that could be maybe vector w or something, right? And if I know that, then I can just do the area of the parallelogram times vector w, or the magnitude of vector w, and that gives me the volume of the parallelepiped. Okay, so that's just conceptual. That's why we even care about the cross product. Some of you physics people had already kind of made some connections with some things in physics about why we might care about that cross product. But anyway, here's another physical example of something that you could use it for. All right, go on to the next video and we'll do a little bit more.